Welcome to Texas State University's Chemistry 2330, Introduction to Organic Chemistry. I am your guide, Dr. David Irvin. We will continue with Chapter 1, Part 4. Now, once we have those electrons in different little shells, we want to talk about how the electrons affect the shape of the materials. And so what we do is we use what we call electron shell valence shell electron pair repulsion. Now, what this means is that because the atoms are surrounded by that electron density and those electrons have negative charge and therefore repulse each other, by putting them in different orbitals, they want to be as far apart from each other as possible. So based on that, by seeing how many regions of electron density we have, that controls the shape of the molecules. So for example, if we look at something very common like the tetrahedral shape of methane, we have 4 equivalent orbitals that spread out as much as they can in a 3-dimensional space, which means they're each spaced out approximately 109.5 degrees. Okay, so this happens whether those electrons are bonded to another atom or are an electron pair. So for example, if we look at methane here, we have the 4 atoms that it's bonded to are in that tetrahedral shape. But if we look at the electrons in this ammonia atom, the electrons are still in a tetrahedral shape, but the bonds make a pyramidal shape. And if we look at the electrons in water, the electrons are in a tetrahedral shape, but the bonds make it a bent shape. So we have to keep in mind the electronic configuration versus the molecular configuration. So in the electronic shape of all of these 3, we have them being tetrahedral electronic shape, but have different molecular shapes. Okay. Now, if we only have 3 equal regions of electron density, for example, some other hybridization or this ethylene here with a double bond, we actually only have 3 equal regions in space, and the only way we can spread those 3 equal regions in space around systematically is they would be 120 degrees apart. You can't spread them out any further than that in a 3-dimensional space. And so what we see is this becomes a trigonal planar. So we have a center atom, and then we have 3 things spaced out as evenly as possible, which means each of those bonds or each of those regions of electron density are trigonal planar. Okay, so we can see that when we have 3 things bonded to the carbon, this center carbon here is trigonal planar because it has 1, 2, 3 things bonded to it. And this central carbon here is also trigonal planar because it has 3 things bonded to it. So if we look at formaldehyde here, electronically, that carbon right there is also trigonal planar, but it has 3 things bonded to it. So it's molecularly trigonal planar. Now this oxygen right here has 3 regions of electron density around it. It's only bonded to 1 atom, so it doesn't really have space, a molecular difference here, but the electrons are going to be out here and here in that same trigonal planar configuration. Now that makes the net and the molecular shape in both of these cases planar. Okay. Now, what if we only had 2 regions of electron density around an atom? Okay, if we do that and try to do it 3-dimensionally, then that would be the 2 be directly apart from each other or 180 degrees, which makes it linear. Okay, so if we look at the molecular shape of something like carbon dioxide or acetylene, the 2 regions of electrons density, this one right here and this one right here, are in a linear configuration. Now notice that the electron density on these right here would still be trigonal planar, but the molecule itself is linear because there are no bonds in those regions of electronic space. Okay, so let's take this up a little bit further, okay? So in the shape of molecules, again, let's look at the electron density and the bonds, okay? So if we look at just the electron density in methane, we have 1, 2, 3, 4 regions of equal space, meaning they're going to be spaced out 109.5 degrees. degrees. And we have 4 atoms in each of those spaces. We have an atom in each of those spaces giving us 4 bonds. So each of those bonds is equal, therefore those are going to be spaced out evenly at 109.5 degrees. In the case of ammonia here, this unpaired electron here still takes up space. It still has a negative charge. Therefore, it's pushing the 3 bonds down, giving the bond angle between them about 107.3 degrees, that those electrons are still taking up that space and repulsing the other electrons, but the atoms themselves right here form that pyramidal shape, and it stresses it extends the bonds just a little bit, making it a little less of an angle at 107.3 degrees. We see the same thing when we look at water. Again, water has those 4 different electronic spaces giving it that trigonal planar shape, but it only has 2 bonds. And so the unpaired electrons actually push a little bit harder. Remember, we went from 109.5 to 107.3 with just 1 lone pair. Now it's down to 104.5 with 2 lone pairs, okay? So the electrons in those lone pairs actually help us derive what the molecular structure is, okay? So when we go to the trigonal planar configuration right here, again, all 3 of these atoms are all in the same plane right here. And so that when we take that atom, when we take that molecule and tilt it on its side, we see that it's nice and flat right here with those 4 being almost evenly spaced out. Now, the fact that we have the oxygen here and it's a little bit bigger atom than the 2 hydrogens here, it pushes a little bit further away. And so the hydrogens are actually closer together than that 120 degree ideal angle, down to about 116.5 degrees. And the oxygen being a little bigger has a little more electron density and therefore pushes a little bit more against those, giving us a slightly bigger than 120 degree angle found in the system. So the electrons are what's driving the molecular structure and the molecular geometry. In ethylene, because these are almost the same nonpolar bonds, we have a little bit less of a thing. We have the size of the carbon is a little bit pushing them apart a little bit, but we have closer to our 120 desired angle for our trigonal planar structure. Okay. Now, again, if we look at our molecular shapes for the acetylene, they are linear molecules. And if we look down them, we'll see that they are, all the atoms are right in a row in both the carbon dioxide and the acetylene here. We actually, the hydrogen, the carbon to carbon, the hydrogen are all in a linear line. And that's because the most they can ever be out is 180 degrees. And it doesn't matter how big the atoms are at the ends because they are so far away from each other, it's always going to be that 180 degrees. Okay, so let's use our valence shell electron pair repulsion theory and draw our Lewis dot structure and then predict our bond angles. I'm going to do 2 of these and then I want you to go ahead and do the other ones on your own, okay? So I'm going to randomly pick this one and this one right here. Okay, so let's start with this one. If we look at our Lewis dot structure, we know that this carbon has a double bond to this carbon, and we have a hydrogen here and a hydrogen here. Then we have a hydrogen here, and we have a C, H, H, and H. We have no lone pairs, so we don't have to add any additional electrons. And so from this configuration, we see that this carbon right here is, I'm going to change colors here so we can look at this carbon right here, has 3 things bonded to it. So that we predict that the angle here is going to be approximately 120 degrees. The angle here is going to be approximately 120 degrees. And the angle here is going to be approximately 120 degrees. Now remember, carbons are slightly larger. So we're actually going to have slightly larger angles here and a slightly smaller angle here because the hydrogen is smaller in size and shape. Over here, we're going to have approximately 120 degrees in all of these angles here. And this carbon right here has 4 different things bonded to it. So we're going to predict that each of these angles over here, and I'm going to change that to red so we can look at these, are actually going to be at 109.5 angles. These over here are going to be approximately 109.5, where all the others are going to be approximately 120. Okay, so that is the first one there. Let's go ahead and start looking at our next one. Let's draw the structure in black. Okay, this one is going to be a carbon. Oops. A carbon right here, and then it has an oxygen bonded to it, and we have a hydrogen bonded to it, and then we have 3 hydrogens on this carbon. But let's see, we need to make sure we count all the electrons here. This oxygen has 1, 2, 3, 4 electrons bonded to it. We need a total of 8, so we have to put 2 lone pairs onto oxygen here. Okay, now in both cases, this carbon has an electronic structure that's tetrahedral, and this oxygen has an electronic structure that's tetrahedral, which means all of these bonds are going to be that 109.5 degrees apart, 109.5 approximately degrees here. And that means that this right here is going to be about 109 degrees apart too, because electronically, these lone pairs push that to give us that tetrahedral structure. Now, because of the fact that the electrons are not taken into account when we talk about the molecular geometry, that means this bond here is what we would call bent right here, but it's bent at about 109.5 degrees right here. The lone pairs take up the rest of the space, and all of the bonds around this carbon are the tetrahedral at 109.5 degrees. Go through and do all of the rest of the structures, looking at how far apart that they can be, and don't forget the electrons take up space but don't have molecular geometries. Okay, so let's go ahead and think about this molecule here. We're going to study this in chapter 9. However, if we just take our valence shell electron pair repulsion theory, we should be able to figure out exactly what all these different angles are. So if we look at this immediately, we want to say, okay, wait, so individually, this carbon has 3 things bonded to it, okay? So let me draw that in red here. We're just going to talk about this one carbon here, right here. So if that one carbon has 3 things bonded to it and we have no lone pairs, that's going to suggest that this carbon here is now trigonal planar. Trigonal planar, okay? So that means this carbon and this hydrogen and this carbon are all flat in a plane, okay? So let's look at the next one over. I'm going to draw that one in green. This one right here has 3 things bonded to it, and that makes it trigonal planar also, which means that this and this and this are all in a plane. Let's look at the next one over. So this carbon here is also trigonal planar. It's going to be that. So that means that this is flat with this, with flat with this, with flat with this. That's suggesting that our benzene molecule is going to be completely flat and planar. We could actually draw this on its side, and we would see that the carbon atoms would all be in a plane, and then the hydrogen atoms would be the sticking out around the edges here. So by looking at each individual atom and adding them to the next one right here, we can see that we predict that this benzene molecule is going to be flat, planar structure with approximately 120 degrees between each of these angles here, because we started with the trigonal planar geometry. Okay, so now let's talk a little bit more about polar and nonpolar molecules, okay? So we talked about polar and nonpolar bonds, and that has everything to do with the electronegativity difference between the 2 different atoms being bonded. But if we add all the different bonds together, we see whether the molecule is polar or nonpolar, okay? So let's look at this compound right here, and it is carbon dioxide. And we know that oxygen is more electronegative than carbon, therefore it is going to be pulling electron density in that direction. So that is a polar bond, okay? Now, the other carbon to oxygen bond is also a polar bond and is pulling electron density in the opposite direction, okay? So that means we have electron density being pulled in that direction by one oxygen and that direction by the other oxygen. And because they're equal, because they're both oxygen, they cancel out, okay? They're pulling in equal and opposite directions, therefore we have a non-polar molecule, okay? Let's try some other molecules and see if we can't elucidate them right here. All right, so let's look at water here, okay? We have the same thing happening here. We have a difference in electronegativity between the hydrogen and the oxygen. The oxygen is more electronegative, so it is going to be pulling more electron density through that bond. So that means that we're going to have a net dipole going toward that oxygen through that bond, okay? So the other bond here is also going to be polar in the same way. We are going to be pulling electron density toward that oxygen there, okay? So if we took those two vectors and put them together, what's going to happen is we have one vector pointing this way and one vector pointing this way. So the parts that go in these directions will cancel out, but they're both still pointing up, okay? Which means the net dipole of the molecule is going to be pointing up because the net pole is going to be pointing up because the component that pushes to these sides cancel out, but the component that pushes up are added together because they're both going in the same direction. So that's why water is a polar molecule, because it has two polar bonds that don't cancel each other out. And CO2 is a non-polar molecule because the two polar bonds cancel each other out because they're in equal and opposite directions, okay? So can we apply that to other molecules that don't have 2 or 3 or 4 bonds? We can. It'll apply to every single molecule we use, okay? So in the case of this ammonia here, there is, ammonia is the nitrogen is the more electronegative atom, and so we have all of these components adding together right here. Now, the linear components that point toward the nitrogen all cancel each other out because they're each 109 degrees apart, so they cancel each other out. So the only component that goes up toward the nitrogen, we add all 3 of those together, and we end up with a net dipole of the molecule to be up facing toward where the electrons are sticking out, okay? So notice that we take each polar bond, figure out which direction it is pulling based on electronegativity, and then summing those bonds together to get the molecular polarity. So we have to take the bonds plus and add them all together to get our molecular polarity. Okay. So that means that we can have a variety of different molecules, as if they are not symmetrical, most likely they will have some kind of polar unit to them. So if we look at, this is a tetrahedral molecule, and it has a net dipole going to the most electronegative atom, which is the chlorine. The hydrogen components all kind of pull toward there, and then the chlorine is the dominant structure here. We also have polarity in trigonal planar structures. Remember, oxygen is the most electronegative, but carbon pulls a little bit of these right here, giving us our net dipole in that direction. And notice that we have, this is the partially positive side of the molecule, and this is the partially negative side of the molecule. We might be able to use that for reactivity later, so we want to pay attention to that. Now, right here, these are almost non-polar bonds between each other, so there's no pull either way here. There's a slight pull toward the center for the carbons because it is a little bit higher in electronegativity than hydrogen is 2.1 and carbon is 2.5, so it's a little bit more electronegative, but they cancel each other out because they're facing in equal and opposite directions, meaning acetylene is a non-polar molecule. Okay, so using our valence shell electron repulsion pairs, we can see that we have polar molecules and we know exactly where the pole lies in those molecules. So we have polar and nonpolar based on where all the dipoles line up.